The broadcast is now starting. All attendees are in listen-only mode.
Oops. Okay. Hello, everyone. Thank you very much for joining us and welcome to today's GDS webinar. Today's talks are entitled Scientific Machine Learning for Molecules and Materials. And this is Jay Ren from Merck & Company. I am the current chair of the APS GDS, and I am joined here by Professor Skanda Vivek from Georgia Gwinnett College as your co-host for today. Today's webinar will run for approximately 75 minutes with two presentations and each followed by a Q&A session. The webinar is actually designed to be interactive and will work best when you are also involved. So please feel free to submit your questions throughout the presentation. You may do that by typing the questions in the questions chat box, and we will try to attend to your question during the Q&A session. You may also raise your hand by clicking on the hand raising icon. And if time allows, we will unmute you to allow for live interactions with the speakers. At this time, know that all participants are in listen-only mode, and please note that the event will be recorded and made available for streaming on the GDS YouTube channel afterwards. Also on our YouTube channel, you may find all of our past webinars featuring quite an impressive list of researchers working at the interfaces of data science and physics. The APS GDS is the newest topical group within the American Physical Society. We're established just over a year ago, and we're dedicated to promoting data science research, education, as well as broader outreach within the APS and beyond. You can find us through the APS official webpage, through gds@aps.org, and also on social media like Facebook, LinkedIn, Twitter. We have a handle at APS Data Science. You can find us on YouTube as well as our Slack channel. Please feel free to let us know if you have any thoughts, comments, or suggestions. As a young unit, we're here to serve you and would love to hear your voice. Now, I'd like to introduce our speaker for today's webinar. We have two speakers. The first one is Dr. Maxwell Hutchinson. Max is a principal scientific software engineer at Citron Informatics, where he develops and operationalizes statistical and machine learning methods for materials development. He is particularly interested in the applications of domain knowledge and predictive uncertainty in machine learning to address the scarcity of high-quality data, which is common in material science and engineering. Max received a Bachelor's of Science degree from CMU and a PhD from University of Chicago, both in physics. Our second speaker is Dr. Matthias Rupp. Matthias works on machine learning for molecules and materials. He studied computer science and obtained his PhD in cheminformatics at Goethe University in Frankfurt, Germany. He then was a postdoc researcher working with groups from machine learning, physics, chemistry, and material sciences in both industry and academia. On the academia side, he last led the research group on machine learning for materials at the Fritz Haber Institute of the Max Planck Society. On the industry side, his last position was with Citron Informatics as well, which is a startup working on active learning for industrial material discovery and optimization. And currently, Matthias is negotiating the next step in his career. And now, without further ado, I'd like to hand it over to our first speaker, which is, let me see, let me hand it over to Max, and I will give you the presentation right, and you may start when you're ready.
Okay, can everyone see me and hear me?
Yes.
Or see my screen anyways?
Yes.
Excellent. So thank you for the kind introduction. I'm going to start us off by talking about discovering materials and molecules via active learning. So first, a little bit about my background and the perspective that I'm speaking from. I've been at Citrine Informatics since 2016. Citrine is a small company that has really been working to operationalize a lot of the academic research and methods development that has happened both in machine learning and in the new, well, not so new anymore, but at the time new field of materials informatics. So most of the perspective that I'm coming from is that of someone who's worked at a company that has worked on, at this point, probably over 30 discrete projects with lots of different partners, some academic, some commercial, projects of different scales, different sizes and shapes in many different sort of subdisciplines of both materials and chemical engineering. So a good place to start is probably talking about what distinguishes data science, machine learning, and AI applications in molecules and materials from any other field. This is a big table. I'll stay on the slide for a little bit if you'd like to read through it. But the short answer is a lot. There are a lot of differences between the application of data science, machine learning, and artificial intelligence in scientific domains generally, and I would say specifically materials, informatics, and chemical engineering that distinguish it from applications of these methods in other fields. The two that I want to focus on today are data volume and the prediction task. Data volume is pretty straightforward. When we work on projects, we often start with on the order of 10 data points. We have had successful projects that got up to 30 data points. If we get up to 10 to the 3 or 10 to the 4 data points, we're usually really happy, and that project is usually going to be pretty successful. This is a really stark contrast to the types of machine learning applications in speech recognition, in image recognition, in big fire hose data stream outlier detection that really have driven what I think is the core of the machine learning community and machine learning methods development. That's actually not, I think, the thing to focus on today because data volume is sort of obvious, and I think that recently, in the last couple of years, there has been a bit of a renewed focus in statistical learning techniques that are really meant to address data volume by working a little bit harder in order to get the most out of the data that we have. And I'll speak to that a little bit later on, but I really want to focus on this third row, the prediction task. In traditional ML applications, you have a lot of data, and you're usually looking for patterns within that data. When we're doing discovery, which is really focused on the materials or the chemicals that we're looking for, rather than the underlying theory, we really want to predict extreme or irregular or abnormal materials. We want to find things that aren't behaving consistent with our expectations. And that really presents some challenges for machine learning. Machine learning works best when you have a lot of similar examples in your training data, and you're just looking for basically, what's the most similar? How do I sort of fill in the gaps? How do I interpolate? And machine learning models are incredibly effective and incredibly accurate in that regime. But when we're doing discovery, we're fundamentally looking for something new. And if it's new, it's probably not similar to anything in our training data. So when you put these two aspects together, you can't really avoid the conclusion that you can't do discovery with machine learning, at least not in one shot. And one shot here is really the weasel word and the way that we get around this problem. Now, I add typically as well because sometimes you get lucky, and there are certain types of applications that are related to, for instance, substitutions, where you're more similar than it seems, and that's why the thing seems more new than it is. But in our experience, at least, the common case is that our machine learning models are not particularly effective, especially at the onset, at actually making predictions on the things that we're interested in. So how do we get around this? We use active learning or sequential learning, or this is closely related to another type of learning called reinforcement learning, which is the thing that all of the game playing AIs do, AlphaGo, the one that plays StarCraft, et cetera, et cetera. And in active or sequential learning, or also reinforcement learning, the key is that your method has the ability to ask the world about itself, to collect more data. or at least to ask for more data. So the basic loop is here below. Let's start at the top. We have a model. The model says, I want to do this experiment. I want to generate this additional data. We generate that data, and then we use that data to improve the model. By the way, can people see my cursor? Can I use that as a pointer?
Yes, we can.
Excellent, thank you. So we start with the model, we suggest an experiment, we perform the experiment, we take the data, we feed it back into the model. Now, if I change the word model to theory or hypothesis, we use a hypothesis to design an experiment, we use the experiment to generate data, we use the data to improve the hypothesis. This really is just sort of science, right? And an iterative process where we do some aggregation of our current knowledge, we put forward some ideas, we evaluate the ideas, and then we refine, but in sort of a machine learning skin. So a couple of technical details, and here I want to leave mostly pointers and terminology to other fields and to other ideas that you may have come across. When we do active learning, we're typically alternating between two important, often computationally intensive tasks. One of them is the training of the machine learning model, and the other is the optimization of the experimental design, the search for the best experiment to perform. Model training can often be broken down sort of into two categories. There's online, where you have rapid enough access to data that you want to incrementally improve your model by incrementally incorporating that additional data. Offline is you throw what you had before away and you just build it all over. In materials and molecules, at least at Citrine, we're typically in the offline mode because we don't have that much data and it usually takes a long time to get more. Optimization is the other really important task. Sort of two things about it. One is when you perform optimization, you're not usually just optimizing your figure of merit or the thing that you want, your design criteria. You're usually optimizing some transformation of it called the acquisition function, which allows you to control sort of, oh, I want to learn more about my problem versus I want to hone in and focus on exactly the goal that I have for my discovery. And this acquisition function often incorporates information about uncertainty. The other thing is a surprisingly frequent amount of time, the actual optimization is just an exhaustive search over some discrete space. Often, like the relevant length scales in the design space aren't actually that large, or maybe the focus is on only a relatively small number of degrees of freedom. So this mode, which I usually refer to as screening, I think many people do as well, is surprisingly effective. You don't necessarily need to have a sophisticated optimization process in order to do effective active learning. So to make this pattern concrete, here's one example that we did with a commercial partner, Panasonic. Panasonic was interested in discovering organic semiconductors that had higher home mobilities. So if we start up here, basically we entered the loop in this position. Panasonic gave us a data set. We trained a machine learning model on it in order to predict the home mobility. And then so that's the training part from before. This is the optimization part from before. We generated a search space of different molecular structures. We scanned through that search space to try to find the best one. And then we didn't find one, we found many. We made a bunch of recommendations. And then this part, it's circled in green for a reason. It's really important. We didn't say, okay, and just do these. We said, this is what the machine learning model thinks that you should consider. Why don't you look at them and decide which ones to do? So this process of selecting molecular structures of interest in this case, or generally taking a menu of suggested experiments and then as an expert deciding which ones make the most sense is really important. And often what will happen is there will be suggestions that don't make any sense. And an expert sees it and is like, oh, that'd be a waste of time. I don't want to do that. On the flip side, what will hopefully sometimes happen is a suggestion will be something that the human being, the expert, would not have thought of on their own, but makes sense in hindsight. And it's through that sort of fusion of perspective that this system works so well. So then, okay, we have some molecular structures that we're interested in. They do some MD, they do some DFT, they add it back to the training set. Let's see how this works. So on the horizontal axis, we have cycle number, and every cycle we're performing some number of experiments, but we're sort of suggesting them in batches. There's on the vertical axis, we have the actual hole mobility. This is the thing that we're trying to, maximize. There's a dotted yellow line here in the center. Prior to that line, so for the first 20 iterations, we do not actually use the predictions for designing our experiments. We hold out that signal. We just say, not knowing anything about the responses, here's your design space. Why don't you select some points from the design space to basically bootstrap the training data set. Then after this 20th cycle, we turn on the signal. We start using the machine learning model. One thing you can see, this is probably obvious, is that as soon as we do that, the points that we're suggesting have higher predicted mobilities because we're basically suggesting them based on their predicted mobilities. But also the DFT calculated mobility starts to go from basically 0 to having some points that have non-zero and have useful mobilities. At cycle 32, so 12 cycles after we turn on the signal in this system, we have our discovery. We find a molecule that has a DFT calculated hole mobility higher than any value that was in our original training set. We have done some improvement, and we can see once that happens, it sort of opens the floodgates. There are now many more molecules that have much higher DFT calculated mobilities. And this could go on and on. To make this concrete, they actually picked 4 of these molecular structures that were sort of the output of this active learning on top of DFT process, and went on to presumably do experimental characterization and to file patents. So that's active learning. Sort of in summary, we get around the intrinsic tension between machine learning's inability to extrapolate or struggle to extrapolate and the desire to extrapolate when doing discovery, when finding novel and fascinating and high-performing materials and molecules by doing this iteratively. So how can we speed things up? In other words, well, you'll see. This will be about the models. So Citrine has, over time, developed, I think, a pretty strong philosophy, a pretty strong approach to the way that we do data science, the way that we improve the models that we're using in this active learning loop. I think it was summarized very succinctly by our CTO, Julia Ling. She said, we want to let materials researchers leverage all of their sources of information to make informed decisions in a, not here, but in a digital way, in a rigorous way, in a way that is reusable and extensible. And there are two ways that we do that a lot. There are many ways that we do it a little, but I want to focus on those 2. The first of which is transfer learning. Transfer learning is basically the idea that if I have data from 2 different but related tasks or purposes, if they share some representational information, if they share some form, then there's probably some knowledge associated with one of them that can be transferred to the other, and that can make the other task better. So to give a concrete example, we're going to go back to DFT in a moment, but talking about band gaps, let's say that we have a relatively small data set of experimental band gaps. So we have chemical formulas. We also have some information about processing and some other contextual information, but for simplicity, chemical formula, and we have experimental measurements of band gap. And we want to train a model to predict experimental band gap. Okay. The plot on the right-hand side of this slide is called a learning curve. On the horizontal axis, we have the size of the training set that was used to train the machine learning model. On the vertical axis, we have the performance of that machine learning model on a held-out set, which is never part of this training set. And what we see is what we would expect. The more training data you have, the more accurate the model is, the error goes down. Okay. So, transfer learning. Let's say that in addition to this very modestly sized, right, 350 points, this very modestly sized data set, I also have another data set that is related, but not exactly the same, like DFT band gaps, of which I might have 50 to 100,000, thanks to Materials Project, HFlow, OQMB, et cetera, et cetera. So you might imagine that that data set has some information that would help with the experimental band gap modeling task. And it does, as we'll see in a second. How do we use it? One way that we really like is that we use that DFT band gap as an input to the machine learning model. The machine learning model should really do well if one of its inputs is strongly correlated with its output. So if DFT band gap is strongly correlated with experimental band gap, we should get a better model. Now, how do we get the DFT band gap? We don't want to restrict ourselves to only using this for materials after we've performed DFT or for which we've already done DFT. So we train a machine learning model in order to predict the DFT band gap, and then we use that as the input. So we refer to this as a latent variable approach. So the results are pretty good. So when you incorporate density functional theory at band gaps as a latent variable, the overall performance of the model improves by 20% or so. The black line is shifted down from the orange line by about 20%. The thing that I actually want to focus on, though, which I think is a better way of thinking about this improvement, is these horizontal lines. So if I go to any point on this black curve, and then I go across, what I'm doing until I hit it is I'm saying, using transfer learning, I was able to train a model that was this accurate with this much less training data than this one. So here I can get, with 64 training points, I can do as well as I would have needed almost 150. With 100 and almost 150, I can do as well as I would have needed almost 250. So what this does is it allows us to take other sources of data and use it to buttress, to compensate for a scarcity of the data for the task at hand. All right, that was one thing. Second thing, domain knowledge integration via graphical modeling. So here's another example problem. We have this data set is a very small data set of structural ceramics produced by NIST. There are 310 total measurements, but there are actually only 19 unique compositions. And what we want to do is we want to predict Young's modulus, given composition and really some featurization of the composition, some label of the way that the ceramic was processed, and the temperature. And we do this on this data set sort of in a straightforward way. We get a R² value of 0.64. So we know something about the dependence of moduli, like Young's modulus, on the temperature, at least for ceramics. There's an empirical relation which was put forward in this paper by Wachtman in 1961, which basically, here's the form of the relation. It says that at low temperature, there's a constant modulus. At high temperature, there's a linearly decaying modulus, and then there's some exponential transition between them. The transition temperature is Tm, the slope of the linear decay is B, and the constant value, the value at low temperature is E0. So what we can do, knowing this, is we can look at our data set, 310 points, 19 compositions. We can group them by composition and processing. We can compute these 3 different empirical parameters. And then, instead of machine learning straight to the modulus, we can do machine learning for these empirical parameters. And the nice thing about doing this is we've completely factored out the dependence on temperature. And the dependence on temperature is often a very large scale dependence, right? If you're looking at a reaction rate, if you're looking at anything with an exponential, and here actually it's only linear, if you have data at different temperatures and you don't know what the temperature dependence is, usually your model will just learn how it depends on temperature, and it won't really learn anything about the materials themselves. In this case, because it's linear, it's at the lowest extreme. So we factor out the dependence on temperature using an empirical relation. We have these empirical parameters. We do machine learning on them. That works pretty well. So in this little R² plot, the baseline, this is what I showed last time. When we include the empirical model, we go from 0.637 to 0.664. Not a huge difference, although it is statistically significant. And I'd emphasize that this data set only has 19 compositions in it. So in other cases, we'd often see something a little stronger. Just to sort of call back to what we were talking about before with latent variables, the natural thing to ask as well, are any of these empirical parameters strongly correlated to things that we can compute with DFT? And the answer is somewhat. So one, you can compute moduli in DFT, so those definitely might be helpful. But also, if we read this paper with the empirical relation, they put forward a proposed correlation or a proposed sort of relationship between the parameters B and T and the Green-Eisen and the divide temperature. So we compute these, and here the model improves a little. And I'll be straight. This is borderline statistically significant. It would really help if we had a larger data set. So that's how we, those are techniques that we use to improve the model. But how do we know if the model has actually improved? How do we know if we're getting better in the way that matters? And I'd highlight that these last two examples, I gave RMSE values for one, I gave R-squared values for other. Really, what is the thing that's significant? Well, the thing that's significant if we're doing the discovery isn't the performance of the model, it is the number of iterations we need in order to find a discovery. So here's an example. This is sort of transfer learning. You know, there's a little more graph up here, don't worry about it. But the idea is basically we have fatigue strength, we have yield strength. Once we've prepared a sample, we can probably measure both of them. If we include yield strength as a predictor for fatigue strength, can we learn more about the materials more rapidly? So here, this is not quite a learning curve. On the horizontal axis, read this as cycle number, although it's written as training set size. And on the vertical axis, we have the thing that we're trying to maximize. And in the blue curve, we're not using yield strength. We're only using composition and temper to predict fatigue strength. And in the green curve, we're using both. And what we can see is with this additional information, we're able to discover or find a material at a certain, performance level more rapidly than we would have otherwise. So is this because the model is more accurate? Maybe, but not necessarily. This slide I actually stole from Matthias. We're going to see this slide again in a couple of minutes. But I think it really highlights something significant in the context of active learning. We have two models here. One of them is shown in solid blue, one of them is shown in dotted blue. And we're looking at two different ways that we could ask whether the model is doing well. On the left-hand side, we have the non-dimensional model error. So this is related to R-squared or RMSE divided by something dimensional. And on the right-hand side, we have the acquired frontier points, which I believe, Matthias, later correct me if I'm wrong, is the number of points which were found to lie beyond the efficiency frontier. So we want both. We want this to be big. We want this to be small. And what we see is that the solid line model. Matthias, are you chiming in? I can't tell.
I have been unmuted, but you're doing fine.
Okay.
It is indeed the number of points acquired on or against the original frontier.
Excellent. So on the solid blue model clearly has lower error. You might say that this is the better model, but it's actually less effective at finding points on beyond the Pareto frontier. So what is it that we want out of models when we're doing active learning? I would argue there are three things. The most important thing is a property called asymptotic consistency. If you have enough data, the model should become arbitrarily accurate. It's sort of like having a complete basis set, or like using a variational method. If you don't have this, then you can get stuck, right? You can be systematically wrong and get stuck and never improve. If you have this, then you know that if you work long enough, you'll learn everything. The second property is predictive uncertainty. It's really helpful for this acquisition function if the model has some notion of how certain or uncertain it is about predictions, so that I can say, I don't know, maybe we should collect more data over here versus I'm sure that this isn't going to work. The last thing is sample efficiency, and it's last. This is an ordered list, even though it's bullet points, I apologize. Given asymptotic consistency and good predictive uncertainty, then obviously we want the model that's the most accurate with as little data possible. So in summary, active learning, or what we at Citrine often like to call sequential learning, is able to perform discovery through iteration. It's really just like science. You put forward a hypothesis, you evaluate the hypothesis, you refine the hypothesis, substitute a hypothesis for model. We have two techniques that are, I think, quite effective at accelerating active learning by improving the model quality, and one of them is transfer learning, the other is graphical modeling. And then finally, accuracy isn't really the only quality metric. In fact, it's probably one of the less important ones. The two properties that I would argue are more important are asymptotic consistency and uncertainty quantification. Thank you. Any questions?
Thanks, Max. That was really interesting to see. So there looks like there's a lot of interesting things going on in citrine informatics, and very much at the cutting edge of physics and machine learning, data science, etc. So right now is the time for any of the attendees to ask some questions. I'm looking at the questions panel. Let's see. I'm not able to see who asked this question, but for the transfer learning bandgap problem, how are you doing the transfer learning? Are you using the DFT bandgap model as an initialization for the experimental bandgap model?
Yeah. So we take the output of the DFT bandgap model and we use it as an input. You could think of it as a machine learned feature to the experimental bandgap model. And this structure has two nice things about it. The first is that if there are systematic errors in the DFT bandgap, we don't particularly care. There are systematic errors in the DFT bandgap, but what we care about is the information content of this as a feature. So we effectively, you could think of it as a cancellation of error through the stack. The second is we usually don't do this with one thing. We usually do it with many things. And if we have some good notion of feature selection in the machine learning models, and it turns out that one of these doesn't have a lot of signal in it, we'll usually just ignore it. So in that regard, it's relatively robust. Whereas if you try to do multitask learning, for example, on two tasks that aren't actually correlated, you can often reduce the quality of both of those models because you're forcing them to share some structure that they don't actually share.
All right. Thanks, Max. Are there any other questions?
Hi, Skanda. I see on the questions panel a few more questions popping in. So let me go ahead and unmute Quinn Cunningham, who is having a question, I think. Quinn, can you speak up? I have already unmuted you.
Yeah. Could you just return to the summary page for a moment or two? I wanted to, if you could explain one more time. Okay, so graphical modeling pulls in the expert knowledge, and is it better to start this first or last, or what is a good sequence to perform this sequential learning?
When you ask first or last, do you mean is it usually better to start with a naive model and then refine it through expert knowledge?
Correct.
Is that the question?
Yes.
That really depends. In our experience, working as collaborators with projects, I think the sort of sequence of events that happens on the model refinement, from a model refinement perspective, really varies based on the group and the organization and the type of problem we're working on. In some cases, like if you know a lot about your problem, don't ask the machine learning model to learn it all over for you, right? Give it that initially, give it that structure, and then you can back off. You can say, all right, well, the data that I'm getting actually doesn't look consistent with this thing that I thought it would be. Let's weaken, as we acquire more data, some of the biases that we've built into our model. On the other hand, especially if you're starting with a lot of data, you might want to start with something relatively naive and then look at, for instance, a predicted versus actual plot or some sort of cluster analysis to try to identify regions where the model is performing better or worse, especially inconsistent with the amount of data that you have in that region. And that can tell you, oh, I'm missing a feature, or there's something really complicated going on here that maybe I can do a literature review on and try to learn something about. It really depends. I definitely, though, recommend, and you're right in that this wasn't made explicit earlier, that when you're doing the active learning loop, when you're collecting data and feeding the data back into the model, as a data scientist, you should also be thinking about doing model refinement. How can I look at the data that has been collected so far to change the structure of my model in order to also achieve better results? And you just have to be careful with cross-validation to make sure that you're not overfitting.
Great, thanks. So just one more question. Do you know the theoretical basis for why machine learning for, in this case, finding new exotic materials or exotic properties requires so much less data than normal machine learning when we're just trying to predict common patterns in data?
Why it requires so much less, usually in order to yeah. I do not have a concrete theoretical sort of reason for that. I have a theory, especially for why models, which are often quite inaccurate, are able to still help find materials which represent improvements. If we use that as our definition for discovery, which isn't always fair, but if we do, even though the model might be particularly inaccurate or might be particularly inaccurate in the area that you're interested in, the model is usually much better at saying that the material that you're looking for is not in some region. It's good at excluding regions. So if you have a vast design space, it can't necessarily tell you where to look, but it can tell you where not to look. And if you exclude the impossible, the probable or the improbable is all that's left. Sort of by that process of exclusion, we usually can sort of reduce the search volume to something where we're relatively likely to find an improvement. And then, if I'm not sure over here and I measure it and it's bad, then I'm able to exclude the region around it, usually on some manifold that corresponds to the type of model that you're using, so you know to not oversample that area.
Thank you.
Okay. In the interest of time, let me just go ahead and read a few more questions. The next question came from Albert Bartok Partey. The question is, aren't you concerned about the fact that your machine learning predicted mobilities don't match the DFT predicted ones?
Yes and no, for the reason that I just described, which is that when we're operating at these data densities, there's really no expectation, I don't think, that we are going to be able to accurately predict the mobility of a material that is better than all the previous materials. I think the much better way of thinking about it in the context of active learning is that we can predict the material that is going to be better. And again, often through this exclusion principle that I just described, the model is much better at knowing the areas that you've sampled enough already and telling you to not sample them anymore.
Thank you. I will read the last question live, but I just wanted to ask that right after you answer this next question, can you stay online and try to open up the questions box? I will give you that access, and then you may be able to go in and see the rest of the questions and see if you can answer them as well. Okay, the last question that I will read is from Kevin Shen. It seems like a lot of this work is possible because of a very mature and fairly reliable DFT engine. What has Citron done for soft matter systems where such reliable simulation methods are not as readily available?
Yeah, so the application of DFT in these ways is actually relatively rare among our commercial contracts. There's a sample bias in the examples that I was able to talk about because they're examples that we've done with non-commercial partners, and Panasonic was very kind and let us talk about their example as well. And I think we collaborated on a talk on it. But in many cases, we don't have access to DFT. We often have access to multiple different labels on either the same type of training data or similar training data. So the example of the field strength and yield strength, right? Once I've prepared a sample, I can make many measurements of it. We also often are able to use historical data, sometimes from the public corpus, but often just in the bowels of the companies that we're working with. We always look and we try to find something that we might be able to bring to bear on it. And then the graphical modeling sort of takes a very different approach there. We get into conversations with really deep domain experts, and we try to capture whatever they know about the problem and either express it via dependencies or independencies, right? This doesn't depend on this. This does depend on this, or empirical relations like the one I showed.
Awesome.
But DFT is an incredible resource, and we're really happy that Materials Project and OQMD and AFLOW exist. They're great, and we've done some work on doing on-demand DFT calculations. We've also done some work on trying to understand the information content and quality of those respective databases.
Thank you so much, Max. Now let me change the presenter right to our next speaker, Matthias, and Max, I will give you a right to be able to see all the questions and enter your answers. So our next presenter will be Dr. Matthias Rupp. And please proceed when you're ready.
Thank you. So you should be able to hear me now. Can you also see my slides?
It is white.
Wonderful. I cannot see my own slides, but yes, that changed just now. Great. So let's get started. Since Jiren also already introduced me, I'll just jump right in. This talk will be about prediction errors of machine learning models, and it will be a lot about non-standard procedure there. The talk is structured as follows. There will be a super brief introduction about surrogate modeling, and then I have 3 questions that I want to talk about. How to model prediction errors. So what about predictive uncertainties? What about the noise model? Then how to assess prediction errors. Metrics that measure also how good the uncertainties are. Which forms of cross-validation to use. And finally, about the distribution of prediction errors. So how are they distributed as a function of the input or feature space, and can we exploit that? And I'll conclude with some recommendations from my point of view. So if we are talking about machine learning models for molecules and materials, there are two realms there, let's say. One is experimental data and one is computational data. And I want to talk a little bit about those two. First, what they have in common. Labeling, so determining, for example, properties of molecules and materials is expensive. In the laboratory, it's human work time, reagents, equipment. And in the computational domain, it is running large, expensive numerical simulations. So that naturally leads to the small training sets that Max has already addressed. And to come briefly back to the question that we had there, I wouldn't say it's not that the question is not how our models are getting away with that few data. It's by necessity. As Max said, they would be much better if we had more data, but we don't. So it is a restriction that we have there. And we have to deal with it. We have to make the most out of these small data sets. At the same time, there are large input spaces. So, right, if you think about molecular structure graphs, for example, if you think of them as colored graphs with some constraints, it's easy to enumerate them. And people have, and that's a space that grows combinatorially. In the computational domain, if you think of a molecule with an atoms, we have 3n-6 coordinates, And that is a large a space that grows very fast. So we enter high-dimensional spaces here. And we want to search those. We want to predict properties in these spaces and find interesting points, molecules, or materials. And finally, there is almost always covariate shift. That means the data set on which we evaluate or apply our models to is almost never has the same distribution of data as our training sets where we created our models. And that, I'll come back to that in more detail, but that poses its own challenge. These are the commonalities, but there are also important differences. For example, in the experimental domain, we have incomplete information. If you think about it, if you have an experimental measurement, often you cannot be 100% sure what is in your sample. And for example, for alloys, where impurities, very small impurities can have large effects, this is an important factor. And also experimental, the data almost always comes with strong measurement noise. If you think of biological cell assays, for example, you could easily have 2 or 3 orders of magnitude of noise. So there can be very strong noise here. And even if you have accurate measurements, there's still always some noise. Whereas in the computational domain, we have by definition complete information. We know the inputs that enter the simulation. So we know that we know everything that is required to produce the output. It's just it takes very long. And also we almost never have noise of only very little noise. So, and then in this setting, we want to build in surrogate models. We want to build machine learning models, for example, that predict one or more properties of molecules or materials, and then we want to search these spaces using these fast machine learning surrogate models. That's the background. And now let's get right at the actual topic, the prediction errors. The first point I would like to make is that point-wise estimates are not very useful. So if you think about it, the usefulness of any prediction depends on its reliability. This is clear in the active learning scenario that Max described, right? The acquisition function requires a predictive uncertainty, a measure of how reliable a prediction is. However, in human assessment, it's also clear. If you are an experimental person and a machine learning accountant says, my model predicts a 10% improvement in the property you're interested in, with a 5% confidence, that's a completely different statement than if you would say with a 95% confidence. And these statements will lead to different actions. So it's important to know how reliable a prediction is. So where does uncertainty in predictions come from? Well, some part of it is due to the models that we build, right? Nature is not a linear regression model, for example, right? We have a specific form, like a forest or a deep neural network, and this model is not reality. There are some limitations due to the form of model that we choose. For example, the kernel function in a Gaussian process. And there's also uncertainty from lack of training data. So, and even if you imagine a homogeneously sampled data set, like the QM9 data set, for example. If you are at the border of the data set, still you will have fewer data available than when you're in the middle. So this is always there, this phenomenon. And finally, we can have some numerical uncertainty, for example, if we stopped our convergence of a neural network early, but that's not the topic of today. So we need, instead of predicting, let's say, a scalar, we need to predict the distribution for that scalar. How do we do that? How do we even represent that? And there's the full scale of possibilities there. The most general is you can, for example, predict arbitrary distributions by, let's say, predicting the cumulative distribution function in a discretized form. But that is usually not necessary. But what many people do is you can predict, for example, a prediction interval. You'll say with 95% probability, I believe the true value to be in this interval around my prediction. Or you can use a parametric distribution, like a Gaussian process. The prediction of a Gaussian process is by nature a normal distribution. So that's one way to do it. And if you don't have a Gaussian process, usually people use ensemble models. You just train several models and different predictions approximate a distribution. This is very frequently done and tends to work well in practice, especially for neural networks. So that is one aspect. The other aspect I want to talk about is noise. So the typical ansatz that we have in machine learning models is we model the observed value y at the location x, let's say the molecule x, as the actual value f plus a noise term epsilon, where epsilon is very often assumed to be independent and identically distributed, usually normally distributed. However, the noise in non-synthetic data sets is all but that. It is not IID Gaussian usually. For example, this real noise tends to be correlated. Imagine you're doing an experiment and you measure in batches on a plate. There will be correlation between all the measurements done on the same plate. Heteroscedasticity. Some inputs can be harder to measure than others. This is clear for experimental data, but also for computational data, for example. If you include heavier atoms, the need for relativistic corrections becomes stronger. So that if you don't have them or a too simple form, then depending on which atoms are in your molecules, the error might be larger or smaller. And there are many other aspects, like it can be asymmetric, the error. It often has broader tails than the normal distribution, which tapers off exponentially quickly. There are outliers, all of that. I want to show just one example here on the right-hand side, the figure. This is an analysis of a data set, experimental band gaps by Stillo and Cook from the literature. And here we have multiple measurements per material. So we are in the nice position to know the experimental distribution. And what you see are two curves. One that tries to explain the noise in the data with the homoscedastic noise model that you usually use, IID Gaussian noise. And the red one is heteroscedastic noise model. So there can be different variants for each data point. Of course, that model is much more flexible, and we could say that we expect it to be on the horizontal, on the diagonal line, where the best one is. But what this shows here is that mostly the blue line is not there. A homoscedastic noise model in this case cannot explain the noise in the data. So that's something to keep in mind. Now that we have talked about the predictions themselves and that they should have uncertainty and a better noise model, how do we measure how good these predicted distributions are? And I want to start with an example that gives a degree of quality for the whole first set of predictions. So if we have the usual predicted versus actual plot, but each prediction has also error bars, let's say like one standard deviation interval. And these are 10 observations, for 8 of which the actual value lies within the predicted interval, and for 2 it doesn't. So we have an 80% coverage probability in that sense. Okay, what we can do now is we can compute the difference between the observed coverage probability and the expected coverage probability. And that, let's call this the deviation from the coverage probability. And here in this particular example, on the horizontal axis, you see the training set size, and on the vertical axis, you see this deviation from the expected coverage probability. Two algorithms, Gaussian process regression and random forest. Now, if you would look only at the absolute value, they would look the same. But if we look at the sign, we see that they actually exhibit quite a different behavior. So the Gaussian process has too large values, which means the coverage probability is too high, which means it is underconfident. Whereas the random forest has the opposite behavior. They are too low, so it's overconfident. Its prediction intervals are too small. It's too sure of itself. And this is an important insight into, on this data set, how these two algorithms behave and their uncertainties. There are many more metrics that are aware of the uncertainties. I'll just very briefly show 2 of them, because they're used often. One is the negative mean log predictive density. This works as these are now judging individual predictions from your model, not a whole set of them. So let's say you predict, like, have a Gaussian process, and you predict for each prediction you have the normal distribution. That's what you're seeing here in the leftmost column. And the middle is the value that you predicted. And the vertical dashed line is where the actually observed value is. And then you just go there and look at the density at this point. And that's the predictive density. And take the log sum and whatnot. So this is a local rule because you only look at the density of this single point. And one can show that up to some equivalence class, this is the only local proper scoring rule where you can look up what the proper scoring rule is, some theoretical properties, which are nice. Now, so far so good, right? This is known and used. What is maybe not so obvious is that this metric, for example, can be gamed in some cases. in a competition, Kohonen and Sumela showed how to win as part of this competition by exploiting a weakness of this metric. If your regression problem has only a finite number of possible outcomes, what you can do is for each prediction, you predict a very thin slice of probability around each possible outcome. And then, no matter which outcome actually happens, you always have high density there, and your metric is doing very well. So that is clear in retrospect, but far from clear, I would say, at least for me, when you initially look at this. A second metric I would like to briefly highlight is the continuous ranked probability score. How does this one work? Well, again, you predict a Gaussian, let's say, with your Gaussian process, for example, or with an ensemble. Here's your prediction. Here's the vertical dashed line is again the actual observation. And what you do now is you compute first this cumulative distribution function of your predicted Gaussian. That's the solid black line here. And then you place a delta distribution on the actually observed value. It's basically, in some sense, the best thing you can do. 100% confident it's exactly this value. And then you compute, that's a shaded area, the difference, square difference between these two. This is a non-local rule because the whole distribution is being judged. It is also a proper scoring rule. And if you look longer at the formula, you'll see that in some sense it generalizes the mean absolute error. Unfortunately, because it generalizes the mean absolute error, it's also much correlated with it often and doesn't give so much additional information as one would have hoped for. Right, there are a lot more of this. For example, in weather forecasts, people have looked at such metrics for a long time. I just want to briefly mention that you can also take statistical tests and turn them into such metrics. Yeah, so that's a large choice here. Now, even if we have a metric with how to judge our predicted uncertainties, how should we evaluate our model? Well, this is also a bit independent of the predicted uncertainty. Let's take a look at this example, because we were talking about active learning and new data. If you do standard cross, so this is showing two principal components axis. These are all molecules, and the colors and symbols show different chemical classes as assigned by the chemist. If you do a normal cross-validation, you will split up this, let's say, into 10 different chunks of data, train on 9, predict the 10th, and iterate through. So if you do that, there's a high chance, no matter which point is in your validation set, that there's a training point nearby. And your model error, your estimated model error, will be quite optimistic. However, in a real scenario, active learning scenario, or in a real screening scenario, virtual screening scenario, let's imagine these green points are the new points that haven't been seen in training, and you want to apply your model to these points. You will have trained on this data, then you will predict these green points, and there's no training point close by, which means your error will be high. That is, your estimated model error will be way off and way too optimistic. So this is something that happens very often, not on purpose, but because people don't inadvertently do this, and if you stop at the retrospective validation, you will never find out. So this is something to keep in mind. What you can do about this is, if you're doing a virtual screening or if you're doing active learning, you can use a leave one group out cross-validation. Take your data that you have, divide it into clusters or groups, preferably with domain knowledge, but you can use clustering if you have to. And then leave a whole group out, and then you will get a much more realistic error for this. And since we are talking about bias and misestimates of model prediction errors, I want to briefly highlight this from one of our recent studies, without going into too much detail of what this plot shows. This is, on the horizontal axis, we have a form of bias related to the size of the molecules in the QM9 dataset. And here on the vertical axis, we have prediction error, root mean squared error. And what I want to show you here is that if you influence this bias inadvertently or advertently, then you can control the resulting estimate of the prediction error over 3 orders of magnitude, 3 orders. In other words, if there is this bias here, your estimation of how good the model is basically arbitrary. So this is important and often not considered. Let me quickly peek if I still have the next slide. I do, great. So what can you do about that? Well, this is from one of our recent works, which we are currently revising. This is a benchmark, and we compare different features for prediction of DFT properties, let's say. And what you see here is a typical learning curve. You see the training set size on the horizontal axis and around the vertical axis, and here are just different representations of features. But the one aspect that I want to show here is we are very careful. We control in this benchmark for the same regression method for every feature method, same way of optimizing the hyperparameters, everything the same. And because we want to see effects due to the representation alone, we are ensuring that the usual assumption of independent and identically distributed data is met here by stratifying our validation and training subsets using multivariate stratification. That means we make sure that the distribution of elemental composition, of sizes, of energies is the same in the training and validation sets. And if you do that in a careful benchmark, that is, and that is what I wanted to say on the previous slide, this multivariate stratification can help you remove this type of bias that I showed in the previous slide. And if you do this very careful benchmarking, you see clear physical effects between the different representations. I will refer you to the preprint for details, but you see what you expect. The higher the interaction order between pairs of triplets or quadruplets of atoms that you model, the better your error becomes, the higher your computation cost becomes. What you would expect, but you can clearly see it in the data if you do careful benchmarking. Now this slide should look familiar. It's the one that Hud showed you already. And let's talk about a bit about active learning. So brief recap what we see here, two acquisition functions, solid line, dashed line. And the left-hand plot shows that the dashed line has a much better overall prediction error. And the right-hand side shows that the solid line, this acquisition function has a much better overall prediction error. And the dashed line on the right-hand side shows that the other acquisition function with higher overall error gets more new and better candidates. So why is that? Why would that happen? Well, here you can see why. These are two output properties that we predict. Electrical resistivity in this data set and thermal conductivity is the other property. And now these are some data points from the data set. Now, what I'm showing here are Pareto shells. The red line here is the Pareto frontier, which means any point on this frontier cannot be improved in one property without degrading the other property. So basically, in some sense, the best points you can find here. And if you remove them and take again the Pareto frontier, you get the next Pareto shell and so on. So we want to minimize both of these properties in this application. So if we want to go to the lower left corner. Now, if your model has good prediction error here, where the Pareto shells are, and bad error here, that's fine, because we don't care about the error here. But if you have great global overall error, but you're not so great here, then you will not find good candidates. And that's the reason for the previous slides, perhaps surprising behavior. So what you can do, for example, you can scope your error towards the Pareto frontier and tell your model explicitly, hey, I want to be good there, not elsewhere. And finally, as my last example, I want to show you, I want to talk a bit about the spatial distribution of prediction errors, by which I mean you can look at just one number, let's say the root mean squared error overall over your whole data. And that's just a summary statistic. It tells you something, but it doesn't tell you, for example, how it's distributed. Okay, you can look at the distribution of the error. Here in this synthetic example that I'll explain in a moment, we see, for example, in the black histogram, we see a distribution of prediction errors. But then again, this doesn't tell you where the error is large or high. And that's what I want to talk about. In this study by Christopher Sutton et al., I took one example, one synthetic example, because it's easy to show, but we have real ones in there as well. Here, the triangles are from the function that we want to learn, which is a polynomial function. And we fit a linear model, that's the plane. Of course, that's a bad fit, right? Because the linear model cannot capture the complexity of the polynomial target function. But there is a strip around values of x1 around here, where the model is quite good. And then it degrades as the function varies. So what the so-called subgroup discovery methods allow you to do is they allow identifications of analytically describable regions in your feature space where the model exhibits, let's say, cohesive behavior. For example, consistently low error, let's say. You can specify that for the method. And that's basically here it finds this strip. And if you look at the distribution of errors, you see that If you only look at the strip, which is the gray histogram, then you see that the errors are all very low here in the identified region, and overall they're much higher. So this can be interesting for analysis of your machine learning. Okay, with that, I'd like to summarize. What the main points were: one should provide uncertainties with predictions. The usefulness of predictions depends on knowing how much you can trust them. So it's good to predict distributions, not just scalar values. One should use realistic noise models. If you can, use a better noise model than IID Gaussian, especially for experimental data. One should adapt the retrospective validation procedures to the problem, to the specific problem. If there's strong structure in your inputs, like molecular series, then by all means take care of that by using, for example, leave group out cross-validation. Or use multivariate stratification if you want a more homogeneous assessment. And also use metrics, or look at metrics at least, that tell you how good your predictive uncertainties are. Not only the errors, but also the prediction intervals, for example, if you have those. And if it's appropriate, scope your loss function to the regions of interest. And finally, it is sometimes insightful to analyze the spatial distribution of prediction errors, so with respect to your feature or input space. With that, I would like to thank co-workers, funding institutions, and the organizers for giving me the opportunity to speak here. Thank you.
Thanks, Matthias. That was very interesting. Very interesting to learn that just simple error is not the story, and there's also many interesting errors associated with predictions. So yeah, are there any questions? So we're just waiting for some questions to come in.
And I'd like to remind everyone that you may also use the hand raising button to have your hand raised, and we will be able to see you. Okay, I see one hand raising. Hold on.
Yeah, don't be shy. Also, I cannot see you, but it's the first time I use this interface. But yeah, please don't be shy. Ask questions if you have them.
I see a hand raised by Albert Bartok Partey, and I have just unmuted you, Albert.
Hi, can you hear me now?
Yes.
Yes.
Okay,
Nice
hi Matthias, thanks very much
you.
for this excellent talk. Just wondering, when you do error predictions with Gaussian processes, isn't it the fact that you find that it almost always overestimates the error? Isn't it due to the fact that your prior is not good enough? Did you have?
Yeah, certainly. Yes, this is basically the question: where does the uncertainty come from, right? Mm-hmm. And in my mind, at least, there are two major sources, sometimes called aleatoric and epistemic uncertainty. So basically, one is from just the lack of data in this case, in our setting, and the other is from limitations of the model. And what you say, having a kernel that is not ideal for the problem, so a prior that is not ideal for the problem, will certainly introduce errors, for sure. Even you can think of super simple models, right? Like, let's say we have a 1D function, like a potential, a two-body potential, just a well and potential well. If you have a single Gaussian kernel, most like 90%, making up this number of models with the Gaussian process use a single Gaussian kernel, right? So it's, or maybe linear is another good contender. But if you have a single Gaussian kernel, you have only one length scale, one. And even a simple function like a potential, like a Morse potential, it has a region where the potential wall is, which changes very rapidly, and a tail where it basically doesn't vary anymore. And you have one length scale, which means it will always be a compromise between the tail and the potential wall, and it will fit neither very well. It will fit the potential well not very well, and it will require way too many samples in the tail. So that's an example of where the Gaussian process is not an ideal prior. And you will see this reflected. If you plot the uncertainties, you will see this reasoning reflected in the predictive uncertainties of the Gaussian process.
Absolutely.
In this particular example.
Thank you. That's great.
But it's just, I mean, this is not yet done that often, right? Or at least my impression is that this is not a standard yet. And yeah, there are many surprises with these predictive uncertainties, I would say.
Thank you. Thanks very much.
So thank you for the question.
Yeah, so Biswajit Santra has a question. How do you determine overfitting of the data? And I'm going to unmute Biswajit to ask that question. Yeah, so Biswajit, go ahead.
Yeah, hi, and thanks for the nice talk. Yeah, that's essentially my question is, I mean, I'm not that much into the machine learning field yet. So my question is, how do you determine overfitting of the data?
Well, okay, yeah, let's have a 3-minute walkthrough of this, right? So if you think of the standard example is, let's think of the 1D problem. We have 1D inputs on the horizontal axis, and we have one output on the y-axis, and these are roughly in the shape of a line, so linear data models. And now we fit them with the model, right? If we fit a constant, then it will be underfitting because there will be large errors. The model complexity of the constant is not enough to capture the linear data. Okay. If we have a linear model, that's great because we'll get exactly the right model. We get low errors, and we'll get low errors both on the training data and on new data, either actual new data or data that we set aside in the beginning for validation. That's proper fitting as we want it to happen. Now, if you take a, let's say, quadratic or higher order polynomial, it will also fit all the points well, but it will start to wiggle in between, right? And the predictions for new data will get worse because of the strongly varying behavior of the higher order polynomials if you fit those. So we will see low error on the training data, maybe even lower than for the linear model, because there might be some noise. But we will see high error on the new data, and that's overfitting. Basically, our model complexity is too high, so that we overfit the data. We reproduce all the training data, but the model is not well constrained between the training data. Whereas with a proper model complexity, we will roughly get all the data right, but we will not start to show irregular behavior so quickly in between. Like for the linear function, will just be stable. So that's overfitting. Now, in the simple example, in the textbook example that we just talked about, this is easy, right? But then you apply to real data, and if this data is more complicated, maybe have thousands of input dimensions, maybe you predict not only a number, but you predict the structure, perhaps, of several numbers or like tensor components. So then, I mean, things just get more complicated, and you cannot easily see all of that anymore. So what you need to do is careful validation. You measure basically like the cross-validation that I mentioned, for example, that all boils down to have some data that was never seen during training data in any way, not for pre-processing, nothing. And then once your model building is finished, predict these held out data and look how good the model is. And that should be your estimate. Right? That's the 101 of the model validation. And even then, that is what I was trying to show. You can still run into problems if you're not knowing. Yeah, it's an often underestimated task, model validation.
Okay, thank you.
Yeah. So it looks like Harrison has their hand raised. So I'm going to unmute you, and you can feel free to ask your question.
If you're speaking, we cannot hear you at the moment.
Yeah, I think they.
No worries. Maybe something happened.
Okay, yeah. Just let me know if you have an unanswered question, but then we'll move to the next question. It's by Abhinendra, and so I'm going to unmute you. Feel free to ask your question. Are you there?
Well, it seems we're out of luck.
Okay, in that case, I'm just going to ask the question. So Abhinendra is asking how good a model has to be to begin with. Should the initial hypothesis be good enough to train? Yeah, this is a question, I guess, about the hypothesis and how does the hypothesis impact the model?
I would in that case, for that question, I would reuse the answer that Maxwell gave before. It depends on how much data you have. So, right, if you just don't have that much data, well, you build the best model that you can and get the most out of it. And that might be less than if you had more data, but that's just what you can do, right? Or you can say, no, I don't have enough data. That also can happen, right? Sometimes you just don't have it. I would say maybe it is good to give an example. There is this area where we try to predict the properties that were calculated using quantum mechanical methods using machine learning models. For example, and my simplest thing would be predicting the formation energies because it's related to stability, and let's see if we can estimate that. Now, you have to have some features that describe your inputs, let's say your molecules, to the machine learning model. And these features, in that area, a lot of work went into these features. The one reference I showed was our own benchmark of the current representations. And these representations, a lot of human effort went into constructing them. So for example, we made sure that the good representations made sure that the physical invariances are respected. For example, if there's no external field and you move your molecule, the energy stays the same. So your features should be invariant to translation in this set. Then again, the same holds for rotation, for reflection, well, it depends on what you're doing, and so on. Sometimes if you predict more than a scalar, you have to be covariant. Okay. And people put all of that into their features to make sure they respect the physics. Now, if you had a lot of data, you wouldn't have to do that. If you're in a situation where you have billions of points, you use a deep learning model and let it learn the features, right? If you just have a simple description, maybe just atomic coordinates, and then you let the network figure out that the properties has these invariances. And that works as end-to-end learning with big neural networks, but it requires orders of magnitude more data. Translation, you can still learn. Rotation, already very doubtful because you need so much data. So by carefully engineering, by putting domain knowledge into the features, we are able to get away with fewer data points. We are better able to deal with small data sets. And that's basically a large part of the work when you have small data sets. Try to incorporate all the physics that you know. Let me give one more example from other people's work. People are also trying to use machine learning to learn, let's say, partial differential equations. And if you know nothing about the equation, well, just take inputs, outputs, and see what happens. But if you know, let's say, a bit about the form of the equation, then you put that already in and just use the machine learning to learn the rest that you don't know. That's the same, putting in domain knowledge. And there's super many examples of that. So that is a very important part of being able to deal with small training sets. Yeah, and then, well, you find out if you have enough data to solve your problem, and if you don't, then you either get the data or you try something else, right? Yeah, thank you. I hope that was roughly related at least to your question.
All right, great. So in the interest of time, let's just take the last question. This is by Quinn. So in relation to surrogate modeling, what would you say are the main differences between design optimization and design space approximation? I'm going to unmute you and maybe you can ask that question live. Yeah, that's not working. So feel free to answer the question, Matthias.
Okay, can you repeat it again, please?
Yeah, so in relation to surrogate modeling, what would you say are the main differences between design optimization and design space approximation?
I'm not sure I understand the question. But that shouldn't stop me from rambling a bit, right? So I think the keywords are somehow the last ones. Design space. Are you there? No. Okay. Design space optimization and design space. What was it? Characterization or something?
I managed to unmute Quinn, so maybe he can ask the question.
Yeah.
Yes,
Yeah.
please.
Thank you. I'd heard of this before and had just known these terms. Basically, the two different applications of surrogate models, and I know that the type of surrogate use depends on the complexity of the problem we're looking at, and so I wasn't sure if you had anything that related to this lecture to add to that.
No, but maybe I'm not sure. Maybe I just don't know this part that you're referring to. So, but however, I would say that there are certainly connections, especially to, let's say, experimental design, right? But if your space is small enough that you can systematically fill it, then you're in a great situation, because then you just place the data where you want information, your training data that you want to measure, in a way that somehow fills that space according to some optimality criterion, and just do that. And that's great, because then your model will roughly cover that space in some sense at least. But if you're in high-dimensional spaces, like, for example, a chemical compound space, then it's first, your space doesn't have this nice Cartesian structure, and it's super high-dimensional. So in the sense of it's large, let's say, and if you have atomic coordinates, then the space will have a high dimension at least, and your points will somehow, your molecules will somehow be distributed in there. And then you can't do that anymore. Then well, you can, but not as easily as before, let's say, right? So often well, I don't want to speculate here, but let's say, at least in my very limited experience in an applied setting, usually you start with given data. Somebody has already measured something. That's because that way they found out that they want to look further. And then your initial set is already given, right? And you can only add points to it. And that is a slightly different scenario to when you're allowed to start, to choose your initial set already. Although now I drifted off a little bit. But yeah, I don't know if this was related to your question at all, but it came to my mind when you talked about the design space, so the space where you're searching in. But if not, then just feel free, if you want to everyone, you can drop me an email. Ask your question later. It's not a problem at all.
Yep. So yeah, thank you, Matthias, for answering all the questions. I do see some more questions in the questions box, but for the audience, if you have follow-up discussions that you'd like to talk to Matthias, he should be ready via email, so please feel free to connect offline. And with that, I really want to thank both of our speakers, and thank you to all of the audience to stay with us and tune into the webinar. And with that, I really want to thank everybody and happy Juneteenth. And please have a great weekend.
Thank you for inviting us. Thank you for listening. And yeah, enjoy. Have a great weekend.
Thank you.
Thank you.
Thank you.